Good afternoon, everyone. My name is Dr. Mohit Chaudhary, and I am accompanied with my colleague, Dr. Ashna Gupta. I'm a senior consultant in transfusion medicine in New Delhi. This is TransConnect, May 2, 2023, and today we'll be talking about secondary hemostasis, which is the second episode on this series of hemostasis. First was the primary hemostasis, which was covered earlier. You can look into that. And once you have done that, this is the secondary hemostasis, which is equally important, and it actually tells you the role played by the coagulation factors along with the formation of the fibrin. So, which is very important for a clot formation. So hemostasis, just to reiterate, it is a dynamic process whereby blood coagulation is initiated and terminated in a rapid and tightly regulated fashion. So whenever there is an imbalance, it may result in hypercoagulable state leading to thrombosis, or it may lead to bleeding, which is manifested as a hemorrhage. There are three components involved in hemostasis. First is the vascular wall, which is the endothelium, and platelets. Both of these comprise of the primary hemostatic plug, but then you also have a coagulation cascade to suffice the stronger clot, which also involves platelet along with the coagulation factors. So what are the steps in hemostasis? We have already covered that in our first lecture, but just to reiterate, uh, vasoconstriction is the first process, followed by a primary hemostasis or the platelet plug formation. This lecture will essentially cover secondary hemostasis or the fibrin clot formation. So fibrin is going to trap the red cells and form a fibrin clot, and this is essentially how the bleeding stops. And last is the tertiary hemostasis or fibrinolysis. So coming to secondary hemostasis, the clotting mechanism, the most important part to remember here is that we want to have fibrin, which is insoluble polymer, and this fibrin is formed from a precursor substance which is soluble or known as fibrinogen. That's why fibrinogen is the first factor that was discovered, and that is why it is known as factor 1 also. Now this happens in the presence of thrombin, so fibrinogen to fibrin in the presence of thrombin. So this is the key reaction of the clotting mechanism. So essentially what happens is whenever there is an injury, the tissue factor which is there on the tissues is exposed to the inner epithelium or the endothelium and to the blood. So that's how the body knows that there is some kind of an injury that has happened. So something which was external, that is on the tissue side, is actually going inside, and there is a phospholipid complex expression. Eventually, through intrinsic and the extrinsic pathway, which are the two pathways for the clotting mechanism, there is a formation of thrombin. And thrombin, once thrombin is formed, it leads to formation of fibrin from fibrinogen. So this is essentially the main mechanism. It is also known as a coagulation cascade, coagulation pathways, and there are both intrinsic and extrinsic pathways. So coagulation, what it is a highly regulated cascade. This word is very important. Cascade of reactions that forms a variety of products involved in hemostasis. So by cascade, it means that the preceding step, the step that was earlier, to the next step becomes stronger and stronger from the preceding steps. So it is like a waterfall or a cascade. So the participants in this coagulation cascade or the coagulation pathways include enzymatic coagulation factors and non-enzymatic cofactors. So what are these enzymatic coagulation factors? These are the proenzyme. These proenzyme are the plasma proteins that circulate in the inactive form. So they need to be activated, and they are mainly produced by the liver. So these proenzyme need to be activated into an active form. Upon activation, they gain the suffix A. So you may have seen 7A or 9A or 10A. So that means that it is an activated form. So production of some proenzyme factor is vitamin K dependent. So it's very important to remember which one of them are vitamin K dependent. These are 2, 7, 9 and 10 factor along with protein C, protein S and protein Z. Then some are calcium dependent and they require interaction with the phospholipid membrane. Coming to the non-enzymatic coagulation factors, these are cofactors which are necessary for enzymatic reaction, and these include factor 1, that is fibrinogen, factor 3, 5, 8, high molecular weight kinogen, calcium and phospholipid. So we'll be talking about these when we actually go for the coagulation cascade. So this cascade model was proposed in 1964 by McFarlane and David and Ratnoff, and this is a sequential proteolactic activation of proenzyme by plasma protease resulting in the formation of thrombin, which is the very important step, and which eventually breaks up fibrinogen into fibrin monomers. So the steps in the cascade occur on the phospholipid surface, and they require calcium. So calcium and phospholipid are very important, especially for the formation of prothrombinase complex, which we'll be talking about. So this is an exhaustive slide which explains both the intrinsic and the extrinsic pathway. So please do not get worried about this slide. We are going to break this slide into 3 parts, and I'll be telling you how each one of the things can be remembered. So we will remember it according to the history. So you can see this is the common pathway. Fibrin is actually what we are all interested in, because this fibrin is going to trap the red cell, and this is the final clot, right? So fibrin is all we need. Formation of fibrin, you require that fibrinogen, which is the inactive form, is converted to fibrin in the presence of thrombin. So this factor is known as factor 1, because this was the first factor to be discovered. So fibrinogen is the first factor. And how is thrombin produced? Thrombin is produced from prothrombin, which is the factor 2. So fibrinogen is the first factor and prothrombin is the second factor, factor 2. Now, for fibrinogen to fibrin, you require thrombin, which is the activated form of prothrombin. And for formation of thrombin, you require a prothrombinase complex. Now, this complex, prothrombinase complex, requires 4 players. So what are those 4 players? There are 2 numbers and 2 words. This is very easy to remember that way. So 2 numbers are factor 5 and factor 10, and 2 words are phospholipid and calcium. So this prothrombinase complex, A means enzyme. So this complex of enzymes require that there is a factor 10A, there is factor 5A, these are the numbers, and you require phospholipid and calcium. So once all 4 of them are there, prothrombin will be able to convert into thrombin, and this thrombin will cause fibrinogen to fibrin, and this fibrin is the final clot along with the red cells. So you require fibrin. So this pathway from prothrombin to fibrin is the common pathway. So now we know the common pathway. Now how do you arrive to this? So there are 2 mechanisms. One is the intrinsic pathway and the second is the extrinsic pathway. We'll be dealing with each of them. But before that, you can remember there is something which is happening above the common pathway and something which is happening below the common pathway. Now what is happening below is that there is another factor which was discovered last, and that was factor 13. Now what happened was, sometime even after the formation of clot, there was some kind of a bleeding. So what was this? This was in some specific cases which lacked something called as factor 13. So now what factor 13 does when it's activated is it causes cross-linking of the fibrin, and this cross-linking of fibrin causes the stabilization of the clot. So below the common pathway is factor 13, and above the common pathway we have the intrinsic and the extrinsic pathway. Now coming to the extrinsic pathway. Now this extrinsic means that there is some kind of a trauma. So it is outside the body. So extrinsic means there is a trauma. So whenever there is a trauma, what happens is factor 7 or tissue thromboplastin, which is there on the outside at the tissue side, or tissue factor that is there, that comes inside the body. Now whenever this tissue factor comes inside the body due to the trauma and it goes into the blood, then what it does, it activates the factor 7 into factor 7A. Now this factor 7A is in itself competent to cause a factor 10 to 10A. Now this 10A, if you remember, is a part of the prothrombinase complex, which is factor 10, factor 5, calcium and phospholipid. So once you arrive to this, then obviously the cascade goes down, and through the common pathway there is a formation of fibrin. So remember, whenever there is a trauma, there is a tissue factor which was present on the tissue side. It gets inside the body and gets exposed to the blood, and then it causes activation of factor 7 to 7A. This 7A acts on the factor 10 and makes it activated to factor 10A, which is a part of the prothrombinase complex. So this is how the extrinsic pathway begins. Now this extrinsic pathway is faster, but it's not sustainable. So it's like a smaller pathway which initiates the thing, but it's not very sustaining. So that's why we have an intrinsic pathway. Now, when does that happen? Whenever there is a subendothelial collagen that is exposed, or there is some kind of a turbulence, or there is some damage to the surface which is intrinsic in nature. There is always some kind of a damage happening inside the body. So this, whenever that happens, there is activation of the intrinsic pathway. Now, how do you remember that? It's very easy. You have this factor 10A, which was involved in the common pathway. Now, there are 4 factors that are involved before this. So, 2 factors are above factor 10 and 2 factors are below factor 10, because 10 is already involved. So 2 factor above factor 10 is 11 and 12. So you can see 12, 12A, 11, 11A, and 2 factors below 10, which is 8 and 9. So 8 and 9. So 4 factors are involved. 12 to 12A, it's a cascade obviously. 11 to 11A. Then 2 below the 10 is 9 and 9A, and 8 and 8A. Now 8 combines with von Willebrand factor also, because von Willebrand factor is attached to the factor 8. So nonetheless, so factor 8, 9, 11 and 12 are a part of the intrinsic pathway. So now you have an intrinsic and an extrinsic pathway all culminating into a common pathway, which is then goes down, and there is factor 13 which stabilizes the fibrin, which is the clot, and it causes cross-linking of the fibrin clots. Now this is a very simple representation of the coagulation cascade. Now this coagulation cascade also has some kind of a checks. Now what are those checks? First is this tissue factor pathway inhibitor. Now what it does is, after the trauma, it does not let the activation of factor 7 to 7A. So there is, if factor 7A is not produced, obviously it is not going to activate the factor 10 to 10A, and that is why there is not going to be any prothrombinase complex. The other 2 mechanism is, once this thrombin is produced, there is also a enzyme called as antithrombin. So antithrombin, what it does, it acts on both factor 10 and factor 2, which is the 2A, which is the thrombin. So it inhibits both. So once thrombin is not produced, obviously there will be no fibrin or fibrinogen converted to fibrin. So obviously it will inhibit the coagulation. Other thing it can do is, when there is thrombin is produced, it can also combine with thrombomodulin. So this is a protein, when it acts and combines with thrombomodulin, it activates the protein C and its cofactor protein S. Now these 2, protein C and protein S, are natural anticoagulants. So they cause a break in the mechanism of the coagulation cascade. So they will prevent the coagulation cascade. So this is another check mechanism. That is why whenever you have a protein C or a protein S deficiency, you may have some bleeding tendencies. So these things can actually inhibit the coagulation cascades. So these are the various factors. The interesting thing about this is, first is fibrinogen. We all know this was the first one to be discovered. Then was prothrombin. I spoke to you about this. There is tissue factor. 4th is calcium. 5th is labile. You can see there is no 6. So there is no 6 factor. There is 7, which is stable factor. 8, we all know it is anti-hemophilic factor, or the hemophilia causing factor. Von Willebrand factor. Factor 9 is Christmas factor. Factor 10 is Stewart power. Factor 11 is PTA. 12 is Hagman factor, prekallikrein, high molecular weight kinogen, and factor 13, or the fibrin stabilizing factor, which was discovered almost last. Platelet factor 3 is another factor. So these are the various factors which have been discovered till now. Coming to the cell-based model of hemostasis, for this I would like to call upon my colleague Dr. Ashna, who will be taking you through this very important model of hemostasis, which is actually more pertinent nowadays. And why? Because you will be once you know this cascade, you will directly be able to interpret some of the viscoelastic assay or the point of care testing, which are actually based on this cell-based model of hemostasis. So it is equally important. In fact, this is the model which is now more pertinent for us. So over to Dr. Ashna for the same.
Hello everyone, I am Dr. Ashna and I will be talking about cell-based model of hemostasis. So the cell-based model, it involves 2 cell surfaces, that is platelets and tissue factor bearing cells. This clotting cascade, it is activated by tissue injury, and it is then propagated by enzyme complexes that assemble on the phospholipid membrane surface, which is supplied by the platelets. So the steps in cell-based model are overlapping, but they are not in a series. That is initiation, amplification and propagation. We will discuss each step in detail. So first, initiation. We know that whenever there is a tissue injury, the subendothelial will get exposed. Uh, this tear in the subendothelium will expose the tissue factor and the von Willebrand factor. Now, this von Willebrand factor, we know it will bind to platelet through GP1B receptor. Now this is the platelet membrane which will provide a phospholipid surface where it will get activated, on which the coagulation factors are active. Now coagulation is initiated when this tissue factor will activate factor 7 into activated factor 7A. Now this factor 7A is activated. It will catalyze the conversion of factor 9 and 10 to activated factor 9A and activated factor 10A. So now this is the extrinsic kinase complex, which consists of tissue factor, activated factor 7A, 9 and 10. So why it is called kinase? Because it is catalyzing the conversion of 10 to 10A. So that's why it is called extrinsic, as it is extrinsic pathway, extrinsic kinase. Now the activated factor 7A which is produced, it is rapidly inactivated by tissue factor pathway inhibitor. So only small amounts of thrombin is produced from activated factor 10A. So this is called thrombin spark, as only small amount is produced. Now initiation has taken place. Now we will talk about amplification. Now in amplification, the thrombin that was produced in initiation, small amount of thrombin that was produced by activated factor 10A, it will bind to the platelet surface GP1B receptor. This is the platelet surface membrane, and to this the thrombin will bind to GP1B receptor. This thrombin will activate several coagulation factors, that is factor 5, factor 8 and factor 11. So it has activated factor 5A, this is a factor 8A and this is factor 11A. This is the amplification phase, as the thrombin that has produced has activated the intrinsic pathway coagulation factors. Now this factor 11A, it will help in conversion of factor 9 to activated factor 9A. So this degree of amplification, it is variable, explaining the variable clinical phenotype of factor 11 deficiency. Now propagation will take place, that is factor 8A that was activated by thrombin, it will bind to activated factor 9A, and this will result in the formation of intrinsic kinase complex. Why this is called as kinase complex? Because it will cause conversion of factor 10 to 10A. Now this intrinsic kinase that is consisting of factor 8 and factor 9A, it will cause conversion of factor 10 to activated factor 10A. Now this activated factor 10A, it will combine with factor 5A to form the prothrombinase complex. So just a small revision: extrinsic kinase, tissue factor, factor 7, factor 9 and factor 10. This will cause conversion of factor 10 to 10A. This is extrinsic kinase. Now intrinsic kinase, it consists of factor 9, activated factor 9A and activated factor 8A. And prothrombinase is 10A and 5A. Now this 10A and 5A will form the prothrombinase complex. So what will factor 10A and 5A, it will cause conversion of prothrombin to thrombin, that is factor 2 to activated factor 2A. Now this thrombin, which is produced in large amount, this is thrombin burst. This will convert fibrinogen to fibrin, that is factor 1 to activated factor 1A, which will cross-link these platelets by GP2B3A receptor. Now this clot has been produced. Now there are some cross checks also, like this coagulation is terminated by two mechanisms other than tissue factor plasminogen inhibitor. First is the heparin sulfate. Heparin sulfate will induce a conformational change in circulating antithrombin, and antithrombin it will bind to thrombin and factor 10A, inactivating them. Now this thrombin also binds to thrombomodulin, which is expressed on endothelial cell surfaces, and it will modulate the function of thrombin. That's why it is called thrombomodulin, and it will bind to protein C, activate it, and protein C with its cofactor protein S, it will bind to factor 5A, inactivating it. Now just a summary of cell-based model of coagulation. There are three steps: initiation, amplification and propagation. These steps are overlapping, they are not in a series. So in cell-based model, two cell surfaces are involved, that is tissue factor bearing cell and platelets. So any injured cell will produce tissue factor. If endothelium is injured, it will produce a tissue factor. This tissue factor will bind to factor 7, and it will cause conversion of factor 7 to activated factor 7A. So circulating factor 7A binds to tissue factor on the surface of cell, and this activated factor 7A, it will cause conversion of factor 9 into activated factor 9A and factor 10 into activated factor 10A. So we have seen this is the extrinsic kinase, which is tissue factor, factor 7, factor 10 and factor 9. It will help in conversion of factor 10 to 10A, and 10A along with its cofactor factor 5 will cause prothrombin into thrombin. So in this, small amounts of thrombin will be produced, and it will be inactivated by tissue factor plasminogen inhibitor. Now in amplification phase, the thrombin that has been produced, it will bind to GP1B receptor on the platelet, activating the platelet, and this thrombin that has been produced, it will activate factor 11, factor 5 and factor 8. So it will cause conversion of factor 5 to activated factor 5A, factor 11 to activated factor 11A, and factor 8 to activated factor 8A. Factor 8 is usually bound to von Willebrand factor, so it will cleave the von Willebrand factor and factor 8 bond, and this generates factor 5A, factor 8A and factor 11A. Now at propagation phase, now the activated factor 11A that was produced, it will activate the factor 9 to activated factor 9A, factor 8A along with factor 9A, it is the intrinsic kinase. It will cause conversion of factor 10 to activated factor 10A. This is kinase, so it will cause conversion of 10 to 10A. 10A along with its cofactor 5A, this is the prothrombinase complex, so this will cause conversion of prothrombin to thrombin. Now this thrombin that is produced, it is produced in larger amounts, so this is thrombin burst. It will convert fibrinogen to fibrin, and this fibrin will cause cross-linking of platelets with the GP2B3A receptor. So this is the cell-based model of coagulation. Now, how does the cell-based and the cascade model differs? In cell-based, we have seen first the extrinsic pathway get activated by the tissue factor, which generates the small amount of thrombin. Then this thrombin, it binds to platelets and activates the coagulation factors in the intrinsic pathway to produce the thrombin burst. So in cell-based model, two cells are involved, that is platelets and the endothelium. They both control the coagulation. While we have seen that in cascade model, the extrinsic and the intrinsic pathway, they work independently and meet at a common endpoint. So they both can produce a large amount of thrombin to form the clot. So in this cascade model, coagulation factors, they control the rate of coagulation, and the platelets, they are only the phospholipid surface. And in cascade model, we have also seen the factor 12, it activates the intrinsic pathway. But in cell-based model, there is no role of factor 12. Now we will discuss the basic coagulation test. APTT, this is a reflection of intrinsic pathway, and the prolongation of APTT, we should consider intrinsic pathway coagulation factors like factor 8, factor 11, factor 9 or factor 12 deficiency. PT is a reflection of extrinsic pathway, and prolongation of PT are usually due to factor 7 deficiency, and common pathway, that is deficiency common pathway factors like factor 5, factor 10, thrombin and fibrinogen, they both prolong the APTT and PT as they are in the common pathway. So this is the cascade model. In this extrinsic pathway factor 7, intrinsic pathway we should consider factor 12, factor 11, factor 9 and factor 8, and in common pathway where both PT and APTT are prolonged, we should consider factor 10, factor 5, thrombin and fibrinogen. Now tertiary hemostasis, fibrinolysis. Now the clot has formed. Now there will be release of tissue plasminogen activator that will cause fibrinolysis, and we have seen thrombomodeling also, the thrombin that has formed, it will activate the thrombomodeling, and then thrombomodeling will modulate the function of thrombin. It will cause activation of protein C, and protein C along with its cofactor protein S, it will inhibit factor 5 and factor 8. Now this tissue plasminogen activator, it will convert plasminogen into plasmin, and this plasmin will degrade the fibrin clot into fibrin degradation products. Thank you. This is all about cell-based model and the cascade model of coagulation. Thank you so much.